first things first, production engineering was very simple in the old days. What it is used to be is about decline curve analysis, and it was just basically monitoring the basic parameters in the well, for example, like wellhead pressure, wellhead temperature, and of course the flow rate. However, um, once you proceed in time, you will find the old methodologies are not sufficient for you. What you need to do is to come up with intelligent and intuitive methods of monitoring and assisting your production system, so you can drive much more production from your hydrocarbons and decrease the problems as much as you can. So basically in this webinar, we will talk about like different aspects of optimizing your production engineering system, in addition to the different aspects of modeling and different types of model we are currently using in Iraq and in other places as well. So let's say this is like a universal language. It's same as drilling, same as reservoirs. Every production engineer should understand this, and it's the same working environment everywhere, except for the operating condition, of course. So as Mr. Ayaz said, I started working with Schlumberger. I started as a drilling engineer, and then I moved to production engineer and then production operations. I worked with different clients, and then I co-founded a company with the ex-Schlumberger colleagues, and now I work as a consultant and instructor for production engineering. So the agenda for the day is we'll take a look at the oil and gas fields in general, so we all be on the same ground level. And then we'll talk about the energy and the different types of flowing well inside an oil and gas field. And then we will take a look at the representation of the pressure drop, or the mathematical equation of pressure drop. And then we'll talk about the influence of the temperature on our different environments inside oil and gas fields. And then we'll start to dive in the very meaningful and very current stuff, which are the modeling of production and injection system. And then we'll take it further and look at the real-time production modeling and evaluation. And then we'll talk about another higher level, which comes after the real-time, which is the integrated production using API and SDKs. And then finally, we take a look at the beast in the room, which is the transient solution, which is like this relatively new thing that has the key to like a great challenges and great problems in oil and gas production. And we'll start from there. So if we take a look, this is on the right-hand side. This is a, well, not to scale. This is an oil and gas field, okay? So in a typical oil and gas field, what you have is a number of producing wells, could be oil, could be gas producers. And these are interconnected and linked using flow lines, okay? And these flow lines are linked in its term with a greater flow line that's known as a header. So it connects all of these flow lines together. So you have just one inlet to the processing facilities. That's the main purpose. And after the processing facilities, you will have tank farms to store the different products that ends up from the processing. For example, you will have tank farms for the water disposal, and other tank farm for oil production. However, this is the configuration on the land rigs. Offshore platforms will be slightly different. You might not have a storage tank there because the space is limited. You will have flow lines that pumps the produced hydrocarbons from the offshore to the onshore platforms. Okay, so as a production engineer, what we are mainly concerned with is these three. Well, number one and number two, most of the time for like 99%, and sometimes the processing facilities comes into play whenever you have like an intriguing problem you need to solve. But mainly we production engineers, we live in both of these categories, which is the oil and gas wells. If we imagine this rather strong man on the right-hand side, if you can see, he's pushing a barrel, an oil barrel. However, if this man lifts his arm and stops pushing, the oil barrel will not push itself, meaning that it will not have the enough energy to move. And it's the same case in oil and gas industry. There is a key energy that makes our oil move from the bottom to the top, or from the wellhead to the different processing facilities, or from the processing facility to the consumers, to the loading station, etc., etc. So this energy in oil and gas is known as a pressure. And you all might know that this pressure actually it decreases with time. And once it decreases, it introduces two main challenges for us. First of all, it's not easily replaceable or replenishable. And if you do that, it will not replenish it at 100%. Plus, it will be cost involved with the process. And whenever you have less pressure or less energy, the problems will start to accumulate on your production system. That's actually a fact. It's no need for the speculation. Whenever you have a pressure drop, you will have problems introduced to the production or injection system. So let's take a look at the different types of wells that's flowing inside an oil and gas field. You will have mainly two different categories of wells that produce money for you. For example, you have oil wells, you have gas wells. Oil wells could be a conventional black oil, or like intermediate or heavy or even light oil. These are conventional black oil. There is nothing special to it. And we have this volatile oil. And in the gas wells, we have three different categories, or three main categories. We have the dry, wet, and condensate. Speaking about the oil wells, these wells could be either pumped or naturally lifted. Pumped means like it's working on artificial lift. Gas lift works as well as one of the methods to lift a well. So the idea behind the gas lift is, or artificial lift, is whenever you have the decline in pressure, you should have another method that's used to lift the oil from the bottom to the wellhead. So this is the basic idea behind it. And regarding the gas wells, there is a common problem that's associated with it, which is the liquid loading. Whenever you have a wet gas, or you have a condensate producing from the well, what these things does, actually they start to accumulate, and the particles collide with each other, and the size of particle gets bigger, and thus the gas will not be able to efficiently unload the well, and those liquids start to deposit on the bottom hole. What it will actually do, it will decrease the production of our well. Let's take a look at how the energy is being dissipated in our production system. The production system, actually, it starts from the reservoir. The reservoir is the very vital part of the production system. If you have good reservoir, you will have less problem. If you have an ill and sad reservoir, you will have actually much more problem you need to deal with on the surface. So the production actually starts from the reservoir, and the fluid travels to the perforated zone. Okay, and there is a pressure drop here, which we will call it flowing bottom hole pressure, or it's denoted as PWF by SPE. And we have another pressure drop along the path of the well. In this image, it's a deviated wall, but it could be a vertical well as well. It does not matter. You will have a pressure drop there. You will have additional pressure drop at the wellhead itself, because you have installed a choke there to control the flow. It will induce a pressure drop. You will have to deal with that as well. And you will have additional pressure drop on the gathering line or the connecting flow line that takes the produced hydrocarbons from the wellhead to the processing facilities. So mechanically speaking, there's three types of pressure drop that's happening inside a given production system, which includes the reservoir, from the perforation up to the processing facilities. You will either have a pressure drop due to gravity, or because of the friction that's happening between the fluid that's flowing from the wellbore, or you will have a pressure drop to the acceleration. I think the part of the gravity and friction is well understood. However, the pressure drop due to acceleration might not be understood. This actually mostly happens when you have highly compressible fluids, namely gas. What happens here, whenever you have the gas that is encountering a restriction, for example, subsurface safety valve or choke valve or whatever, it's the particles will start to collide, and you will have a loss in acceleration in the in the area before the valve, and you will have an increase in acceleration after the valve. So this will induce a pressure drop in the restriction area. However, this acceleration term is mostly negligible in liquid producing wells. We talked about these three terms that makes a pressure drop. Let's see how we can mathematically represent those. We have this equation that's called the mechanical energy equation. I am sure some of you guys have already seen this. Okay, this mechanical energy equation is sometimes called the general energy equation. It consists of three parts. You have the pressure drop due to elevation. Okay, this is number one. Number two, due to friction. Okay, and number three, due to acceleration. This is most of the time is considered zero. Whenever you have a pressure drop due to elevation, it's very, very simple to calculate, especially for the vertical wells. It does not need anything. You only need the density and the angle of the well, plus the depth. This is actually the same equation as hydrostatic pressure equation. It's used in drilling. It's the same with different units. And another equation we have is here is the pressure drop due to friction factor. This is known as the Darcy-Weisbach equation. This equation actually it's simple to solve, but there's a couple of challenges we need to work with. The first thing is the density. Well, you might think why the density is challenging for us. Actually, in the single phase wells, density is not challenging. If you have a water well, for example, injection, the density is rather constant. So you don't need to worry about that. And in the gas well, you have the PVT data, or if you have the correlation, so you can calculate the density with the depth and with the pressure variation. It becomes challenging when you have multi-phase flowing in the well. For example, if you have water, you have oil, and you have gas, and sometimes you have produced solids you need to deal with. So you need to calculate a specific density that represents all of these phases. So it becomes challenging there. So we have like different tricks that can do that. Most of the time, what we do, we calculate the equivalent density, which is the density of the specific fluid divided by its fraction in the flowing region. And we have the friction factor. This friction factor is a beast on its own. There is a lot of controversy and a lot of different opinions about the friction factor. However, most of the used friction factor comes from this chart. This is known as the Moody diagram. I'm sure most of you guys are already familiar with if you have taken course in fluid mechanics and similar courses. However, this is for the smooth pipes. Okay, and sometimes you don't have smooth pipe, you have like an aging pipe of 50 or 60 years old. So this chart actually does not represent that case. So you need to look elsewhere. However, this friction factor, actually it's building in most of the software, so you can't do anything about it. How this chart works, actually you have two keys here. The first key is the Reynolds number. You need to calculate the Reynolds number. It's very easy to calculate. You need the density, you need the velocity, you need the diameter of the pipe, and you need the viscosity. And then you need to calculate the relative roughness of the pipe. Actually, most of the controversy lies here. The roughness, actually, it's very hard to calculate. Actually, I'm not aware there is a specific way to calculate the roughness. most of the ways to calculate the roughness is through measured profilers. You have like these devices that calculates the inner roughness of the wall. This is like it's look like a pig, and then you insert it in the relative roughness equation, and you actually come here, and then you project the Reynolds number, and then you will get the friction factor. Okay, the greater the friction factor, the greater the pressure drop you will have inside the pipe. We always try to minimize this value. You have to minimize the friction factor. So on the picture on the right hand side, actually I took this picture. This is a 4-inch gas pipeline. This was in service for 45 years, and then it was cut out of service. This pipe is carbon steel pipe, 4-inch inside diameter, and you can see actually the corrosion that happens inside the pipe. Actually, it's not the corrosion I care about. You can see how much roughnesses that have added to our pipes. So these are some of the pipes you need to work with when you work as a production engineer, because you will have a lot of uncertainty regarding the friction factor you will get. So let's establish something. The roughness increases with operational time. So as much as you're operating your pipe or your well, the same goes when I say pipe. Actually, I mean the tubing, the casing, or the surface conduits for like flow lines, etc. Plus, the roughness is it's hard to know precisely. There's a number of correlations that you can calculate roughness with it. It all requires the Reynolds number, by the way. You have the Colebrook equation. This is an implicit equation, meaning that it needs iteration. Actually, this is approximation of the Moody diagram. We have the AGA equation, American Gas Association equation. This is mainly used for gas wells or gas pipelines. And we have the Swami-Jain, which is an explicit, which is very used, and it's very easy to use, and it's simply you can program it inside Excel. And it will give you a result closer to this one. It's mainly used for liquid. So this is liquid, and this is gas. And by the way, you can use the Moody diagram for gas as well, but it will have like a certain degree of error to it. If we take a macroscopic look to this area, which is encircled in red, you can see there is like a profile change in it. This is the roughness that does the friction and reduces the pressure. This is a case I've worked with like a couple months ago. This is for a specific company that has an export line, which is in a hilly terrain in Iraq. Actually, what the company is doing, they are running simulation, and they are not getting the results they are required. For example, whenever they are doing matching between the inlet and outlet pressure with the flow rate, they are not getting consistent results. Actually, the reason come to find behind that, they are operating a 50-year-old pipeline, and this pipeline has wear and has pitting inside it. So what you need to do is actually to collect operational data over time, and then you need to match it with the new friction factors. So what I have identified on minimum is 4 types of friction factor that's happening inside the pipe. And this friction factor actually changed from every 5 or every 10 years or so. You can see on year 5, which is the black line, the operating condition on the inlet was 820 PSI. And whenever you are coming on year 30 on simulation, you will see an increase on inlet pressure of 25, 23 PSI. The reason is that actually means you need to pump more pressure in order to deliver the same amount of oil, meaning that you will have more pressure drop due to the friction. Actually, this data was calibrated with 2 or 3 years of operational data, so we can drive this conclusion. whenever you're working with the production or injection system, you have to consider the work environment as well. For example, in Iraq, we have a lot of dry sand environments, and they are very, very hot. The temperature reaching 55 and 57 degrees Celsius on the hottest days of the summer. And we have another regions in Iraq, which is the Kurdistan. Actually, the temperature goes like below minus 10 or minus 20 degrees Celsius. So you need to keep an eye for the environment you are working with. For example, because whenever you have a colder environment, you will susceptible to the flow assurance. You will have more asphalt in deposition, more hydrate if you're operating with gas wells. And then if you are working on the deserts, actually you need to watch the gas lines, because the gas line, the pressure increases with the increased temperature. Actually, I've seen gas lines it's connected to a safety valve, and the safety valve actually opens up because the increased temperature. It's not like because of operational error. No, because of the temperature, the pressure of the gas line increases. We have a specific field in Iraq. Actually, it's located on North Iraq. It pumps heavy oil. It produces around 28K or 25K of 14 to 15 API. This field actually, its production on the summer is around 30,000, and during the winter the production declines to 22,000. This is 8,000 or 7,000 difference actually is due to the temperature change, because you have a viscous oil. Whenever you have a viscous oil, you will need much more pumping pressure and pumping capability. So that's why you need to watch out for the environments. Actually, we are done with the basics here. We should all be on the same page. Now we will talk about production modeling and why we need this. Okay, you already now know what a production system is. Now let's talk about the modeling. So let's say you have a well, gas or a liquid well, producing liquid. Actually, you need to put this inside a computer model to generate an understanding and to put your operational data in it. Once you have this model, actually you can do a lot of amazing and creative things with it. You can predict the future, and you can unlock or unleash the capabilities that no one have seen. And plus you will have much more sustainable production, and you will mitigate or eliminate the problems altogether. So this is basically what a production model is. So let's see what's the data, or let's see what the minimum data you need to create a production model. You will need the well mechanics or the wellbore diagram. This includes the casing, the tubing grade and tubing sizes, and the subsurface equipments you have lying in the well. The second category, you will need a PVT properties, which is the fluid properties flowing. You need that. Either you will have PVT data from lab tests, which comes in handy, and it's much more accurate, or you can use correlation, or you can use equation of states. Actually, it all depends on the type of fluid you have. However, most of the time we are satisfied using correlations if you have already calibrated the correlation with PVT data. And then we have like the most annoying part of the production system management, which is the reservoir or the inflow part. This is like the highest degree of uncertainty we have in production model. Because of most of the well tests that's conducted, they are expire like in a month or so, because of the production environment is changing and the operation condition changed. You have to have regular pressure surveys. For example, you need pressure buildups, or at least you need to know the average reservoir pressure, because if you have like a 2 or 3 or 5% error in that, actually it will comes to be a lot of error in your production value. Plus, you will have the production, the reservoir temperature, which is important. However, it's not that important to know, because you already have the geothermal gradient in different types of wells and different parts of the world. You can utilize that, and it's pretty close. And regarding the operational data, you will need the tubing head data, and you will need the wellhead temperature data. You will need the casing head pressure, and other data you will have is the back pressure reading, which is the the gauge after the choke, and you will have the different artificial lift parameters if you have them installed in the well. It's already if you have already recorded it, it's very handy to put it in the model. Plus, you will need the choke size as well. So these are the basic production data actually we need to model our production system. The same thing goes for injection well. However, you don't need to monitor the temperature of injection well. And in addition, you don't need to monitor the flow rate that's going inside the injection well, because you will have another method of calculating the flow rate if you don't have meters to it. I'll show it to you in the upcoming slides. So now comes the hard part, how to decide to model your production system using a given software. You have two different types of softwares you can use. You have either the steady state simulators, which is the types of simulators that assumes the production or the operational environment and operation condition does not change with time. And these softwares are Pipes and Prosper, Perform, and even Gap to some extent does that. And then you have the other type, which is the dynamic state or the transient state simulators like Olga, LidaFlow, Gap Transient, and you have a new product coming to the scene called Meet from Paradigm. These types of software, actually, they assume nothing is constant. Actually, everything is changing in your environment. So they are very handy to use. And however, they require much more input data. And plus they are much more expensive. So as you can imagine, not all of the companies have those types of softwares, especially the transient state simulators. Actually, small companies, they do not have even the steady state simulators. They do it through Excel. So once you do your production modeling, you will start to generate some data. And how to know if your data is efficient and your result is good? Actually, you need to ask yourself some questions. So, is your pressure is good? Is it accurate? You need to know that. And how much the reservoir pressure have changed over time. For example, the past couple of years, how it's changing. You need to know how accurate your well test data is. This is a very vital part in any production modeling. Some well tests actually they get unvalidated very soon. For example, like in a month they change. Is the tubing size is good enough for your well? For example, I have seen one of the cases. Actually, it was condensate well, and the wellhead temperature and sorry, the wellhead pressure was declining very fast, like in couple of weeks. They come find out the reason behind that. They are producing liquid with it, and the liquid is not being loaded efficiently. So it was accumulating on the bottom of the well, and it finally make the well die. And actually, the solution to that is very simple. You can do it in Excel sheet. It's related to the tubing size. You need to make your tubing smaller, so it will have less cross-sectional area and thus much more higher velocity that will unload your well. You need to ask yourself, corrosion-wise, how well am I doing? You need to know that as well. For example, you can have mechanical corrosion because of the very fast production, especially if you are producing sand. And is there any slugs forming inside my well? And what's the duration of the slug? And at what temperature, what pressure they are forming? And how many they are forming in a given time period? So you need to answer those questions as well. You might find a well that's producing, let's say, 5 or 6K in Iraq. However, you might find it's have severe slugs. This is not a very healthy practice. It will reduce the life of the well, and it will affect the surface facilities. if you are working with gas wells, what's the potential for hydrate formation? So you need to know that as well. In addition, is your well being unloaded? We mentioned that already. This question was related to the production wells. And regarding the injection wells, they are much simpler. That's why you will actually see there's like a little bit of monitoring inside the injection well, because they do not generate any money per se. Of course, they are inject inside the reservoir, which increases the overall efficiency and overall recovery factor. However, currently, when you inject water, actually you are losing money because you are operating a well that's not productive. Let's just leave it at that. So what you need to do with injection well, actually you need to monitor the wellhead pressure. You need to monitor the bottom hole pressure if you have any gauges installed, which I highly doubt people are doing that. How much is flow rate or injection rate you are reporting, and how much is being calculated from the software? Actually, you need to match that. You need to match and tune your model. Knowing these data, actually, you can really find out what's happening inside your well. It's all related to this factor here, the bottom hole pressure. Whenever you have a bottom hole pressure increase in any given injection well, this means one of the two things. Either your configuration of tubing is not sufficient, you're producing pressure, or there is a skin damage that's happening inside your well. And whenever you have the bottom hole pressure decreasing, meaning that you have channeling, or your well is performing much better than you think. These all actually require all operational data to monitor and measure. So let's see what toolboxes we have. We have the nodal analysis. This is for the production engineers. This is like the grandfather and the godfather of all of the plots. What you have is two things that's plotted. You have the inflow from the reservoir, which is this one, and you have the outflow from the reservoir. What you do actually is you create a node inside the well. This is the bottom of the well. This is the bottom of the well, and this is the fluid coming from the reservoir. So this is known as the inflow, and the fluid leaving that node is known as the outflow. And the intersection between them gives you the wellhead pressure and the flow rate. So this is the basis of our model matching and model creation. You might have pressure profile and pressure drop profile. This is basically used for deviated wells or horizontal wells, and you can even use this for the surface connections as well. You have this chart, which is known as the matching chart. This is you select multiple correlations, and you will project your measured data, and then each correlation you will see how much is closer to your measured data. So you can come up with one correlation that fits your well and gives you the most desired result, which is we are talking about the measured versus calculated data. And we have the unloading chart, which is specifically for gas wells, wet or condensate. This chart actually shows you how well you are loading your well, and if you are operating below or the above the critical velocity of the gas wells. So, Mr. Ayaz, how am I doing regarding time-wise?
Yeah, it's perfect. Thank you.
Okay.
Okay, for the time, and we still have 10 minutes to 15 minutes.
Okay. So now let's change the game, which will introduce real-time monitoring. All of these things we talked about, they are mostly done offline, meaning you would do it on your laptop when you're home on your office, and you match the data and you report it to your supervisors or the person who is supervising the project itself. However, sometimes we have critical wells, you need to monitor them online. What you do actually is connect transmitters to the gauges, and then send those data over seas or over land using wireless connection. and then you will monitor the same parameters we talked about, but this time you will monitor it on the real time. The real time gives you an advantage. You will you will find the problem before it becomes bigger and it cannot be solved and it's out of hand. Plus, you can utilize these nifty warning signs. For example, if you have a well producing under capability or under potential, you will see like these types of red flags. And if you are you have a well which is producing more than its capability, you will see this green stuff. You will have nice dashboards, you will have nice storytelling, and you will know what's happening inside your field each and every minute. Actually, you will have the nodal analysis in real time as well. What this does, actually, this gets the wellhead pressure, wellhead temperature, and the flow rate, and plugs it inside the model, silently calculates, and returns back the results. And you can see how accurate your model is and how accurate you can actually predict the upcoming production days. In this slide, actually, we will talk about like a bit of advanced production modeling strategy. This is known as the integrated production management. Most of the time, whenever you have a software, for example, you have Petrel or you have Techlog, especially you have, if you are working with seismic data or your petrophysics. I don't deal with these type of data, so I don't use them. However, I'm familiar with these types of software. Sometimes you need a specific feature and it does not exist in that software. I'm sure most of you have had that challenge. However, the companies that provide these types of software, for example, Schlumberger, Halliburton, Petex, they started to provide an open part to their software, meaning that you can build your own code and integrate it inside the original software itself. This is known as API and SDKs. Basically, an API, it stands for software, application programming interface or application programmable interface. Those are both interchangeable terminologies. And the SDKs, actually, they are software development kits. The main difference between API and SDKs is that API only, they provide you a code to use. However, SDK, they provide you a code plus an interface to use. For example, if you go to Schlumberger's website, ocean.slb.com, you will see different types of software manufacturers. They are actually selling plugins for Schlumberger's platforms. This is actually done using SDKs. And the APIs, actually, they are used inside the PipeSim, inside OFM, inside Petex softwares, inside the PVTSim software. A lot of software, actually, they utilize API nowadays. So they are very, very efficient to use. However, it requires some programming knowledge. Now, I know I bored you with this stuff. However, let's see what can we do with this SDK and API that the current solutions, it's not doing. We'll go back to this programming languages in the upcoming slides. So first case we have is integrating PipeSim and OFM. This is an actual case. We did it for an actual client in the United States. So what this client actually, he wants to do is he wants to monitor his artificially lifted wells, meaning that gas lift wells or ASP wells, and he needs to monitor it inside OFM. However, he lacks one thing, which is like he has like 20 wells or so. And these wells, he does not have the enough engineering hours to do. For example, in a well, you might need 4 to 5 hours to match and tune the model and get the result. However, what you can do is connect these two softwares using API, and you can push data from inside OFM and create model dynamically inside PipeSim. This is all is done on the background. The user does not intervene, and the PipeSim does that model, generates the data, and report it back to you for the engineer to review. So instead of spending a couple of hours on working on each well, you will actually spend less than half an hour only simulating and reviewing the results. So this is very intuitive and very intelligent things to do. And some companies actually they are already utilizing these types of solutions. Most of these solutions actually they are homebrew solutions or they are uh, done in house. So they develop the code and they do these types of simulation. So these types of simulation you cannot find it actually commercially. Another solution we have is connecting nodal analysis software to a SQL client, which is a database. What SQL is actually for the people who does not know it, actually it's a database engine provided by Microsoft. It's what it does actually. It stores data, and it provides you a little bit of programming languages known as SQL. You can use that to retrieve data. So that's what SQL is. So we connect the nodal analysis model to the SQL and SQL, its term, we connect it to material balance engine. So on the right-hand side, we have this database that contains wellhead pressure, wellhead temperature, and all of these nifty operational data. What you do is actually you insert those data inside the material balance engine. This is all done in the background. The user should not intervene, by the way. If the user starts to intervene, it means your solution is failing and it's not doing its purpose, because the sole thing of these types of solutions is cut man hours, and it's much more accurate and much more efficient to do. So all of these data are plugged in inside material balance engine. And the material balance engine, actually, it reports us only a single value, which is the average reservoir pressure. This is like the high uncertainty value inside the production system models. And then we plug that reservoir pressure with the well test we have. We will generate two types of dashboards. The first dashboard is the production dashboard for the producing wells that being simulated. So you can see this plot. Actually, this is a real case. You have here like 10 wells. They all view the nodal analysis for that well, and you have another report you can view it inside Excel sheet. And we have another dashboard, which is the injection dashboard. This is also done by altering the reservoir pressure. Because the injection wells, they are very sensitive to reservoir pressure. You should not make your reservoir pressure fixed whenever you are motoring injection well. This is not an accurate things to do, because you will think there is a specific thing happening inside the reservoir, and actually you will come to find out it's the quite opposite of that. Now we are done with these types of integrated solutions. So let's see what programming languages we can use. This is actually, it's not up to me and it's not up to you guys. Each software that's provided by the different companies, for example, Schlumberger, Halliburton, etc., they select a specific software, a specific platform, and they provide the software, the programming language with that. So you cannot do anything about it. For example, if you are working with Schlumberger technology, you will need to deal with .NET technology, C#, Visual Basic, and F#. And if you are working with a software, let's say Multi-Flash, you will need to deal with C++. If you are working with Techlog, you will need to work with Python. If you are working with, let's say, with a geolog software, which is a petrophysical software from Paradigm, you will actually need to work with Python, or I think a variation of Python. Plus, some of these softwares, they provide Excel integration. However, the PETEX, they do not provide this type of language. They have their own sets of commands, and they have their own environment to do it. However, it works well and it connects the software as well. So these are the different programming languages the companies provide for you to use it as a integration tool. All of these programming languages are offline, meaning that you will do it inside the corporate or the company. How they will not work online. So there are a lot of set of programming languages that's working for the online solutions. we will not touch it upon on this slides. So um, on the right hand side, we have this athlete woman who's running. She's fast, she's strong. She might be on steroids. So what a steroid is actually is types of pills or injections that some athletes do to enhance their performances. In production modeling, we have a same concept, which is known as transient modeling, which is production modeling on steroids. So what transient modeling they do for us, they cover all of the weaknesses of the steady state and then some more, meaning that you can model and evaluate and understand, and you can even predict, mitigate, and eliminate the problems in the upcoming operational environment and operational condition. Transient solutions, they capture the complexity of the wellbore and the complexity of the wellbore region. This is something that the steady state simulators like Pipes and Prosper, they fail to do. And they fail to do this because this is their own category of the software, and they are not trying to be another person who's hesitant. So what can we do with transient modeling? First of all, the transient models, they are fully numerical model, meaning that there is like a mechanistics part to it. However, they do not rely on correlations. They change with time. The pressure changes, the flow rate changes, it fluctuates. Actually, it represents what we have on ground. It can predict different flow assurance, for example, asphaltene, wax, the naphthanates, and other types of issues. It can work with gas wells. You can tackle the issue of loading with them, liquid loading. You can design your artificial lift system with it. You can monitor it. You can diagnose it as well. And you can actually capture the changing of distribution of phases and the changing of the flow pattern with time. Actually, this is something the steady state software that do not do. Plus, in these types of transient softwares, we have actually an advanced thermal modeling. So let's take the first case study. We have the lazy well. So what a lazy well is, actually it's a well that can produce. However, when you shut down the well, it will stop producing. So actually we have these types of wells in the world we need to deal with. And whenever you close in the well, you will have some of the fluid being injected back inside the well. And the phase starts to redistribute, meaning that the oil column will start to shrink. You may have higher water column or less water column. It all depends on the status of the near wellbore region. But what something is for sure, the oil will start to shrink because the gas will start to evolve from the oil column. This will leave us a semi-dead oil. Oil will get heavier and it will exert much more pressure on the bottom hole. So whenever you come to open the well to the production, actually you will find out your well is only flowing gas and the well will not start up. So this case is known as the lazy well. So how can we do that, or how can we start this type of well? Actually, it all depends on the opening of the how do you open the well? It's known as the bean-up strategy. So we have an actual case here presented in this slide. This modeling is done through Olga software. I will walk you through this chart. So on the left-hand side, this region, this is actually the steady state region. The well was flowing and it was beautifully stable. We obtained a PLT survey and matched that part. So we know 100% it's representative of our actual production system. So on hour 8, we shut down the well for 24 hours. Okay. Whenever we shut down the well, we monitor the water holdup. We did this inside the software. And on hour 32, this is mean 24 hour later from the shutdown, we decided to open up or start up our well. What happened is actually the well did not flow. We have this spike or this initial production came. However, and then the well died like in half an hour or so. This is because of the guys have escaped so fast, so it did not leave a chance for the oil to leave as well. So what we need to do is come up with different strategy to tackle this problem. So what you need to do actually is create an alternative bean up strategy for this types of well. This is actually this strategy that we operated it and it failed to lift up the well. This was like the corporate standard strategy to bean up a well or to bring it online. However, it failed in this type of well. So what we need to do is to come up with a different bean up strategy. So what we did is change the opening sizes and opening periods for the well. For example, you can see we started it with a higher or larger choke size here in this startup, and you can see the well have started to produce. You can see this well is producing from this bottom hole flowing pressure. This black curve actually it represents the well when the condition it was not able to flow. So this is the before bean up, the before the revised bean up, and this is the after revised bean up. And then we can safely increase our choke size in these 2 steps or 3 steps following to that. So once you know for sure your well is it can flow after shutdown. And by the way, this is not for all of the wells, only for lazy wells. You can actually go ahead and safely start your well. To be 100% sure, there is an extra step. However, this is not necessary to do, but there is an extra step you can do is to link a wellbore model or a radial model to your already existing transient solution and analyze the shutdown period inside the simulator. So you will have this nice build-up pressure response here. So you can see how long the shutdown you need for the pressure to recharge in the wellbore region. However, this requires extra steps and extra time to do. Do you guys care to take another case study, or we should conclude this webinar?
If it takes, for example, 10 minutes or 5 minutes, it should be fine.
No, actually, it will take like less than 5 minutes.
Okay, it's okay.
Okay, so one of the issues we have in most of the fields, especially the fields that are undergoing the water flood, is there is a rise of the water cut inside the well. However, whenever you do well test, the well test actually it takes something from like 6 hours to 24 hours, depending, and sometimes 48 hours, depending on the flow properties and the fluid and the rock properties inside the reservoir. However, this 24-hour or 48-hour period, it's not enough for you to notice any different or any change in water cut. However, what our operational experiences tell us, especially the people who are working on production facilities, they know for sure whenever you open up the choke, you will get water cut. Okay, so how can we model that? This is something you cannot do with steady state softwares, for example, PipeSim or Prosper, because for a specific reason, which is the water cut, actually it's a property of the fluid itself in these types of simulators, and it's not a property of the reservoir. So this is the main issue. You cannot use PipeSim or Prosper for this challenge. So what we did is we selected Olga to model the change in water cut whenever you open up or close up the choke. So this is the final model we have from Olga. we can see with different types of choke sizes, actually we get different response of water cut, and let me tell you, it's not linear. Whenever I see linear relationship, especially related to the reservoir, I am not happy. So I extracted the most important information about this, and I've created this choke envelope chart. What you can see is actually it comprises of two curves. This bottom curve, this bottom green curve, this is the oil production, and the upper curve is the water cut. So, and the x-axis is the bean size. So you can see whenever I increase the bean size, actually I am getting more and more water cut. Up to a point, for example, up of time of almost 70, actually you will have more water cut than oil. So that's type actually of charts you should generate with these types of softwares. This type of choke envelope, actually it helps you to decide at what choke to operate your well. For example, if you don't have these types of chart, you can go and guess the optimum choke size, but it will not be your optimum. For example, one of the wells we have producing in North Iraq, they will have a high water cut whenever they open the choke. And whenever they close the choke, the well is not being able to produce. It's only producing gas. So you have this very critical envelope of choke operating condition or operating size you need to be careful with. And you can determine that safely using softwares like Olga or LidaFlow. Because these types of software, actually, they are transient and they change with time. However, first thing first, you have to calibrate your model and then you can do predictions. The reason behind the well dies or the water cut is very important to us as production engineers, because whenever you have more water cut, your well will eventually die. The reason behind that, it alters your traverse curve or deliverability curve. The green curve that's drawn here is of water cut of 10%. This is not actual curve. This is a replica curve, just to give you an idea. This line, actually, this curve have like a nice curvature to it. This curvature actually, because of the GOR or the GLR, it gives you this curvature. Whenever you have more water cut, this curvature will reduce, meaning that you will have less water wellhead pressure, and you will have much more pressure drop due to friction and due to gravity. For example, this curve is of water cut 70%. And whenever you have 100% water cut, you will have something called the static gradient, which you will have this fluid level up this high, and your well will eventually die. This is the reason it's very important for us to know how much water cut we have, because it gets inside all of these different calculations in well bore deliverability and stuff. Come to find out, these types of softwares, for example, Pipesym or Prosper, they do not generate or do not work with different water cuts, which rises with different operational changes. You can do sensitivity with it. However, it cannot predict how much water cut you will have in the upcoming years. It cannot do that. So you can see the choke performance in these types of software. It gives you two things. They give you pressure versus gas rate or versus GOR. This is actually, it helps somewhat. However, this is not satisfactory because it does not tell you how much water cut you will have in this operating condition, or how much different wellhead temperature change you will have, or how much water cut you will get in the facilities whenever you change the choke size. All of these type question, actually, it can be answered using transient modeling. So towards the end of this seminar, actually, I would like to thank you and thank the Technico SPE for having me, and I will be happy to answer any question you have.
Okay, thank you, Nashat. We are now opened for 10 minutes of discussion. If any one of you have a question, you can unmute and ask Nashat directly.
I have a question.
Yes, Sophia.
Yeah, please go ahead.
First of all, great webinar. Thank you. My question is, as a production engineer, what would you say that it's your biggest challenge, the hardest part?
Actually, the hardest part of production engineering, it's related to two things. The first thing is it's a challenge from the 30s and the 40s when we have this analytical stuff, which is the reservoir part. This is very challenging. And the other thing, started to be challenging in this decade, which is the flow assurance, the different types of precipitation we are getting, the different types of hydrate structures we are getting from our production, and the different types of loading we are having in our gas wells. These are the different types of the problems we get intimidated by them, because whenever you do predictions, it might not be 100% for sure, because whatever you put inside those simulators, you will get the result for it. So the simulator does not know if this was correct or not. So there is a saying, garbage in and garbage out. So sometimes the data actually intimidates me as well, because there is a lot of errors in the data. So this is the biggest challenge we are having.
Okay, thank you.
You're welcome.
I have a question too. Regarding the due management sometimes of some companies, we don't have the full records of injection rates.
Okay.
So for example, if you are now as a production engineer, you got some data and you need to evaluate the reservoir now. How you can do that if you don't have all the records and you can't do like a full history matching of the reservoir?
Okay, actually it's relatively very simple to do. However, it requires some programming knowledge. If you recall let me take you back to the pressure drop equation that I have presented. Okay, so this equation actually, you can use this for production or injection wells. The main challenge with the injection well is the absence of the flow rate. Plus you don't have the bottom hole flowing pressure. So in this regard, you have two routes you can go with. Either you have an injection logging tool that you have run previously. You can use that. You will have the PWF and Q from that, and you can build a model. And the only thing you will change in the model is the wellhead pressure, and you will get different types of flow rates depending on the operating condition, because the water is uncompressible and there is like a little, there is no gas to it. The only thing you need to know is the density of it and how much salt and how much equivalent solid it has. So this is the first route, and this is the easiest one because you already have the well test. If you don't have the well test for that, what you can do actually is you will have a meter installed on that well, and you can monitor how much flow rate it's going inside that well. And then you will remove the meter. You will record the wellhead pressure, and you will record the flow rate. Whenever you record these two things, you will have only one thing left unknown, which is the bottom hole pressure. You will calculate the bottom hole pressure, and then you plug this inside your model, and then you can calculate and predict the future performances with it. There is another method you can do, which is known as the two-gauge method. You should have sufficiently long pipeline for injector well. It should have two gauges. Whenever you are injecting with a specific pressure, you need to monitor these two gauges and get the readings. You can plug it inside this equation, and it gives you the flow rate. The flow rate actually, it's not very accurate. However, it's a good approximate of what you have. However, you need to tune the friction factor as well. Hope this answers your question.
Yeah, thank you. Any more questions?
Yes, I have a question, if I may. May I?
Yes, please.
Yeah, sure. Go ahead.
So thank you very much, Nashat, for this amazing presentation. It was really nice. A bit too much, like it's a broad,
Thank you.
wide knowledge. Yeah. So I have three questions, please.
Yes.
The first one related to the corrosion, and you mentioned to the uncertainty. I would like to just, if you don't mind, elaborate more about uncertainty. Is it about petrophysical uncertainty, modeling? You speak about that, please. And the second
Yes.
one, you mentioned the monitoring of injection rate, and you mentioned that there is no gauge or device to measure this injection rate. Can you also explain that in a more
Yes.
details? And the last point is when you spoke about the choke size, and you have mentioned that you're increasing the choke size to get more, or for the lazy wells to be in, productivity, to get production out of it. Are you not afraid for water cunning? And if yes, what's the steps to avoid this? This is
Okay.
my questions. Thank you.
So let's start with the first question. The first question was related to, just give me a keyword.
Corrosion and the
Okay.
uncertainty, please.
Okay, so the main uncertainty that corrosion introduces. So actually, let me show you an illustration of what an actual corrosion is looking like. So this is a 4-inch pipeline. The pipeline should be smooth, okay? The pipeline or the tubing or the production casing, it should be smooth. Whenever you have corrosive fluids or corrosive gases inside your hydrocarbon, what it does, actually, there is a chemistry going on here, and it will start to peel the iron, and you will have metal loss. Whenever you have metal loss, for sure, for 100%, this metal loss will not be uniform. So you will have corrosion patches here, there. What it does, actually, it increases the inner wall roughness. Whenever you have this roughness increased, you will get like high uncertainty. So in these steps, what can I do? Do I need to segmentize my pipeline?
Mhm. Okay.
So
Yeah.
I did segmentize my pipeline. How can I calculate efficiently the friction factor? Okay, this, if I did segmentize it, this means I have multiple friction factors for each of these segments. Actually, you can do that. However, it's very challenging to manage, and it actually requires a lot of operational data, and you need to have multiple gauges to record these types of segments.
Okay.
So does that answer your first question?
Yes. So the uncertainty is related to the corrosion itself, nothing
Yes.
else, like petrophysical property. Okay. And the second one was about injection rate, and you mentioned that you don't have a monitor on
Yes,
the
yes.
well. Yes, please.
Okay, so what I meant by that, injection wells, actually they are run on cheap cost. You need to minimize the cost for the injection well because they are not making any money for us. So what they do not do is they do not run bottom hole gauges for them. You only have the wellhead pressure gauge, okay? So you need to work with that. Along with the wellhead pressure, you will get a flow rate from the pumping station. You will allocate these values. Now you have 2 points, which is the Q, the pressure. What you can calculate is the bottom hole pressure. So that was what I meant when I said they do not run gauges, bottom hole gauges for the injection wells. They do using injection logging tools, and this is not so often. They might do it every year or so in the best cases.
Okay, so you have an injection rate, and from the reservoir or from the production wells, you calculate whatsoever, and you get more or less the pressure within in the reservoir, correct?
Yeah.
Perfect. And the last question was related to the choke size. You mentioned to increase the size of the choke size itself, and you get more productivity or more production from the well.
Yes.
Are you not afraid of the water conning of water cut? If yes, what are the steps to avoid exactly to avoid the opening the choke size to access the limits and avoid the conning? Yes.
So, Dr. Karan, I'm 100% sure you are already working with reservoir simulators. Am I right or wrong?
Yes, I am.
Okay. So I am not a reservoir engineer. However, I have some information about that area. So what do you do inside the reservoir so it can give you the deliverability for your reservoir? You will input the VLP curves. Am I correct?
That I don't know.
Okay, so let's assume you have a specific reservoir model and you want to produce from that reservoir. What you need to do is you insert all of these type of wells and all of these configuration. However, how Eclipse or CMG calculates the pressure drop inside the well itself, it uses something called the vertical lift curves, correct?
Okay, go ahead. Yeah.
Okay, so the main issue with these types of curves, actually, you have to generate it using Pipesum or Prosper softwares, and they are not transient curves, meaning that the operational condition does not change during the simulation.
Okay.
Let's put that in mind. That's why you need to use, for example, tools like Olga. In Olga, you can build a rock model and attach it to your wellbore model. In this term, you will have two dynamic models. The first dynamic model is the radial model. You can have it any extent you like, maybe 1.5, maybe 2, maybe 3 kilometers. It's all on your preferences, and you can distribute the saturation in it as well.
Okay.
You will put the wellbore inside it, and you will optimize your choke sizes based on that. So whenever you have the well choke optimized, actually you can monitor what's happening near wellbore. So in that area, you will 100% for sure know if you are having conning or you're not having conning. So the key answer is yes, you can use Olga. However, you need to attach a rock model to it.
Okay. So let's say I have a case right now. It is one of the fields in Iraq, in north of Iraq. Probably you're aware of that. The water production is huge, like 12,000 barrels to oil production is 8. Most probably it is water conning. If it does, can any further studies to be done and to save the field? Are you aware of such as, yes?
Yeah, sorry, please continue your question. Sorry.
Yes, so if the field is damaged, let's put it this way. I know a field right now in north of Iraq. It's being completely damaged, and it's a shame. And yeah, this is my question. Are you aware of some people, professionals, or related study in a way to save the field?
Okay, so basically what you need to do is you need to run PLT inside the well and produce the well maybe with different choke sizes if your budget allowing you to do so. Whenever you do that, actually you will find what types of perforations you are getting your production from. Let me actually show you a case I have here.
Yes, please. That would be amazing.
Okay, so what you need to do is, do you see the screen?
Yes,
a new
I do.
screen?
Yes.
Okay, so what you need to is run PLT inside your well, and you need to identify the perforations that are producing these waters. And if you identify these successfully, what you can do, actually, you need to intervene in the well, and you need to shut off these perforations. Okay, maybe you can do acid injection or acid cleanup for the well as well to increase the productivity. However, if all of these perforations are watered out, what you need to do is look for another zones that you have net perforated that's containing oil. And if all of these perforations actually they are watered out, there is no other layers bearing oil, actually I'm afraid you cannot do much about that. Either you can produce the well with its capacity, maybe you are having 70 or 80% of water cut, and you just have to deal with that.
Okay, yeah, thank you very much. It's so
You're
clear.
welcome.
So let's say bye-bye to the field. Okay, thank you.
Okay, thank you. That's it. We will end the webinar now. Thank you, Nashat, for accepting our invitation and also for such a nice presentation. And we are looking forward to host you again, maybe in the future.
Thank you. Thank you for having me.
Thank you. Thank you also for all of the engineers that attended this webinar. And we would be happy to host you again in our upcoming webinars.
Thank you.
Thank you.
Thank you very
Bye-bye.
much.
Bye-bye.
Bye bye.